Good evening, everybody, and welcome to tonight's Tech Talk. This evening, we'll be talking about database management with Arthur Sato and Wesley Jia. Take it away, guys.
Thanks, Ryan. And I'd like to take this moment to thank SingleSprout and CoSmith for hosting this event. So we're here today to talk to you about some database management strategies. On the agenda, we'll talk about the problems with the lone database deployment, some replication strategies for that said problem with the deployment or set of problems, some use cases for these replication strategies, and we'll wrap up with a little talk on database partitioning. So, okay, so you've got a single database. We're all good, right? I would say not. And for one, the lone database serves as a single point of failure, so our fault tolerance is pitifully low. If the database goes down, we're going down, and our application is going down with it. It requires vertical scaling, so to add more capacity and more CPU and more bandwidth to the database to handle more requests requires a high cost instead of a linear cost. It would scale exponentially. And then with these high volume of requests, the bandwidth gets flooded and it creates a lag. And all of these problems contribute to overall low availability of our data, which is less than optimal. So thankfully, we have database replication to help us out with this. So we would have a primary database become what we call a leader node, and then we would be replicating that data to a replica node. And we've solved our single point of failure issue, leading to greater availability of data. And we're now in the horizontal scaling realm where we don't have to scale upwards, but we can scale out, adding more machines. And adding more machines is, again, scaling price-wise linearly as opposed to exponentially with vertically. And so before we talk about some strategies for replication, I'd like to just go over a couple, or actually a few ways that we can read and write data in this format. So traditionally, we could have the client read and write to the leader node, and then the leader would replicate data to the replica. If we have like a more balanced read and write ratio, maybe 1-to-1-ish, we could have the client write exclusively to the leader and the client read exclusively from the replica. That's if the read-write is even. And if it's more read heavy, the client could split reading between the leader and the replica while writing exclusively to the leader node. And so with that said, let's take a look at asynchronous and synchronous replication. So in the synchronous replication approach, we have the client writing to the leader, and then the client will not receive a success response until the leader has successfully written the replicated data to the replica. And with this scenario, we know that the data is safely replicated in the replica. But now we have added another processing point for the data, therefore adding to our overall latency. And problematically, if the replica were to go down, we wouldn't be able to get a successful write as we need to get a success response. It needs to be replicated in the replica. So alternatively, we can use an async replication approach where the client writes to the leader and immediately gets back a success response, and then later the leader would replicate the data to the replica. And we've boosted our performance, and we're no longer at the will of the performance of the replica. But we're weakening our guarantee of data durability. So if the leader were to receive that write and then respond successfully, but then for some reason go down afterwards and not replicate the data, we'd have inconsistency between the data and leader's data. So What happens if a leader goes down, you say? Well, we'd have to institute a failover strategy. So, failover strategy is basically a plan for what happens if the leader goes down. And there's a few ways we can handle this, and we'll talk about a couple. One is the replica would become the leader. So to follow the chart, if the leader fails, while the leader is rebooting, the replica has been promoted to the leader and will take all the requests. And when the former leader has successfully rebooted, it will take its new place as the replica to the new leader. And in an alternative strategy, we will have the replica as temporary leader. So we pick back up where the leader is rebooting after a failure. Upon successful reboot, the former leader would receive a dump of data, and then upon complete data dumpage, the leader would be re-promoted back to leader, and the temporary leader would be demoted back to replica. So it would seem like we're doing pretty good. Maybe we've covered all our bases, but I know you know what's coming. We really haven't solved all of our issues yet. The leader is still a bottleneck for some requests, creating edge cases of low availability, and there's still the question of vertical scaling to deal with. So I'm going to actually maybe call on someone in the audience to maybe help me out with what they think a strategy to help us out with this might be. How about Tyler? Tyler, what do you think we should do here in this situation?
I would guess some kind of load balancing. Like it looks like you've got a lot going on all at one point, but can you spread it out?
Yes. In fact, that's exactly what we're going to do. We're going to horizontally scale. You nailed it. So we're just going to add more replicas. And with this, we're bringing higher availability to our deployment. And then we're adding, we could add a load balancer to help direct the data right traffic from the leader. How that data is partitioned amongst the replicas we can get into later. There's still some vexing issues, though. What if we were to scale upwards with our organization or app? Say we're geographically dispersed. I think then we come back to that problem of great network latency, and we still haven't addressed the issue of the single leader being a bottleneck. So I'm going to talk to Wesley, or pass it over to Wesley to take care of these next issues.
Yeah, I'm happy to have a conversation if you want, but I guess I'll just present. So thanks, Arthur. And hello, everyone. So let's talk about how we solve this issue. And if patterns have given any sort of indication, we might want to add a second leader node. Let's take a look at that. You just add another leader node. And what we can do is we can place each leader node in closer proximity to each of our clients. So in this example, we have one client who's located in London, another one in the far, far away land of Hong Kong. But by placing the leader nodes in closer proximity to these clients now can experience lower latencies. And additionally, we receive the benefits of higher throughput in our system because we now have additional nodes to support write operations. Additionally, data can be replicated across our leader nodes so that we can ensure data consistency throughout our deployment. Now, that being said, as you can probably also guess, there might be an issue with this. We have to consider the case of what happens if a network partition occurs. A network partition specifically is referencing a case where the connection between two databases might go out. So in reality, the two databases are in constant communication with one another. Leader A is constantly pinging leader B and vice versa to replicate data between themselves and to also just check for a heartbeat. So leader B is constantly messaging leader A, hey, you there? You there? You there? You haven't crashed and burned? And if leader B stops hearing back from leader A, leader B might presume, oh, leader A died. I need to assume control over this deployment. I'm now the sole leader. I need to just make sure everything's working properly. However, during a network partition, it just means that the connection didn't go out. Leader B thinks that leader A is gone when in reality, they just can't communicate with one another. So that brings us to the split brain problem. And if we take a look at the example here, let's say we have a client who makes a write operation to the top leader to increment value by 100. And then we have the same client make a subsequent write operation to the bottom leader to increment it by 50. So value has been incremented by a total of 150, but the bottom leader gets a subsequent operation and thinks that at the end, it's only been incremented by 50. And when you start reconciling databases and putting the data back together, this resolves in some conflicts. Many of you are familiar with like git merge conflicts, so it's not too different in that sense. We could solve this issue with a technique called stonith. And that is a very, very technical engineering term that stands for shoot the other node in the head. What that is it's an aggressive database fencing mechanism where when the system notices erratic behavior with one node, the system just completely takes the node down to just completely eliminate that erratic behavior in the first place. But that being said, there are other approaches that we could take. And if you might have guessed, another answer here is to simply add a third or more leader nodes. So now we have 3 leader nodes and we can see how we can solve the issue. So let's take an example where the connection between leader B and leader C goes out. Well, that's not a problem because they can still communicate with leader A as an intermediary. So that's not a problem. Additionally, we also reap the benefits of higher throughput because we have more nodes to support operations. And we have continued opportunity for geographic distribution and lower latencies. And Rebecca, I'm seeing a pretty confused face over there.
Yeah, so what's to stop us from just continuing to add more and more databases to solve our yeah, exactly.
Yeah. That's a very good point. So right, a lot of you might be having this question. It sounds like we've had a series of problems and the answer every time is you just add another replica or you add another leader. What's the deal with that? The answer is always going to be that it depends. And you really have to understand what your specific use cases, what your business needs are, because adding more nodes is always going to result in greater cost and greater complexity, which is not something that we always want. It's always going to be a trade-off. And in reality, a single leader with multiple replicas is the most common topology. It's not as crazy complicated and it does the job. And there are some cases where we actually don't care about some of the benefits of replication. So you might have an internal reporting tool where if the database takes too long to replicate or serve responses back, you can just say, I don't care, I'll just check again tomorrow or something, doesn't matter to me. Or if all your clients are local to begin with, then why do you even care about geographical dispersion? So it all comes down to what do you care about? What trade-offs as an engineer or a database architect are you looking for? So with that said, we're gonna wrap up replication itself with one more final topic, which is leaderless replication. This is a form of replication where actually every replica is going to accept read and write operations. And in fact, there's no concept of either a leader or a replica. Everyone is equal. And what this means is there's going to be lower latency and higher availability through the system because you have multiple replicas that can accept a variety of commands, and you don't need to worry about failing over from a leader to a replica, which has its own complications because there is no concept of a leader and a replica. And the way this works is that a given client would perform the same read or write operation against multiple nodes to ensure data consistency. There are some rules around that. There are additional safeguards that introduce some complexity. And if you're interested in that, you can check out a topic called quorum consensus, but we won't go into that for the scope of this tech talk. Now, at this point, we've talked about replication. We talked about taking one database and copying it over to others. We do have to consider the case if we look at one specific individual database, what do we do if we have a ton of data in that individual database? Well, one, your response times for that database is going to increase. Your query is going to have to search for more data. You're also going to need to worry about vertical scaling because you're going to need to increase CPU, memory, storage, and so forth, which can cause your costs to just really balloon. And you will have issues with fault tolerance because if all of your data lives in one single database and that database goes down, that might have some horrible consequences. So the last topic that we're generally going to go over today is partitioning. So to solve this problem, you would want to consider partitioning your databases into smaller pieces. So the first technique that we're going to talk about is vertical partitioning, in which you take a large database and split it up into different databases, smaller ones grouped by a specific business topic. So instead of putting all of your data in this example into one giant client's database. You split it up where perhaps the top one is a client's database that just has metadata only for like when they signed up, who's the account manager for that client and so forth. And the bottom one is subscriptions, like what products has your clients purchased from you. That's vertical partitioning. And the other form of partitioning is horizontal partitioning and sharding, which we basically take an overall large database and we just slice it into multiple pieces. They all have the same general content, but they're just smaller slices of the overall pie. And we're just going to talk about sharding for a little bit before we wrap things up. So what we want to use with sharding is to apply it to large data sets specifically for better scaling. There's multiple sharding techniques that exist out there. We're just going to cover two to help illustrate the example. So on the left-hand side, we have algorithmic sharding, which is about a client managing, implementing, and utilizing an algorithm on their own side. And of course, in this case, the client can refer to a server that is making requests against the database. So a client, when adding a new user, might just check the ID of the user they're adding, and based on that, put it in the specific database. Whereas with dynamic sharding, the algorithmic logic is decoupled, where an external locator service is going to determine what shard the data should be read or written to, and the client just sends their normal request. The sharding has benefits of faster query response times. It can allow for horizontal scaling, and we also get to minimize the impact of outages. So if just one shard goes down, you still have your other shards available. It doesn't take your entire database with it. But that being said, sharding adds additional layers of complexities and costs. So this should not really be pursued unless it's absolutely necessary. With that said, we're gonna wrap things up for our tech talk. So as we've talked about, database replication brings benefits in terms of higher availability, higher throughput, and so on and so forth. But of course, there are trade-offs that we need to make with cost and complexity. And as a result, the topology of our infrastructure should be dictated by what your specific business needs are. And lastly, when a single given database becomes too large, you want to consider partitioning it into smaller pieces or shards. And that said, that concludes our presentation. You can find Arthur and I on LinkedIn and GitHub here. We look forward to connecting with you. And just to really wrap things out, here are some resources that you could check out if you are interested.
All right. Does anyone have any questions for our speakers this evening? Whit.
Hey guys, great talk. In regards of partitioning databases, is it best practice to just horizontally or vertically scale, or would there ever be a case that you would want to do both?
Hey, thanks for the question. I think you might be referring to partitioning in this case in terms of which one to choose. I think that's a great question. When it comes to partitioning, you can definitely do both. They're not mutually exclusive. You can definitely take an overall database and split it up into different sub databases organized by different topics. And if any of those are too large, you can also say like, oh, there's just so much out of here. There's like 10, 20, 30 millions of rows in here. And there's and I need to make sure that like this database is reliable and available. So I'm going to then take this sub database and split up in smaller shards. That being said, that should only really be necessary for like the most complicated and largest of database deployments, because one or the other can do the trick. Sharding itself, horizontal partitioning, is really used for very complex deployments to begin with. And at my last company, we had a ton of data in our databases for sure. And to my knowledge, we actually didn't employ any sharding for that matter. And we had significant vertical partitioning only. But they're definitely possible to mix and match together.
Great, thanks.
Great question and great answer. I don't see any other questions. So let's all one last time give Arthur and Wesley a huge round of applause.
Yeah, guys.